In this lesson, we will discuss the Thevenin and Norton equivalent circuits. The Thevenin equivalent of an electrical circuit is the simplified form of the circuit consisting of a voltage source in series with a resistance. So if you are given a circuit such as this circuit, you will see that we have a voltage source. We have about 4 resistances, 1, 2, 3, 4. This circuit can actually be simplified and converted to a Thevenin equivalent circuit. And as we defined, a Thevenin equivalent circuit will be an electrical circuit that has just a voltage source connected in series with a single resistance. So what we want to do with this kind of a circuit, it may even be a more complex circuit, but whatever the complexities of the circuit, our duty would be to convert all the voltage sources into one single voltage source and all the resistances in the circuit to one single resistance that would be in series with the equivalent voltage source. So our duty is to transform a complex circuit, whatever the complexities are, to a Thevenin equivalent circuit just as this. So you see, we still retain the terminal is here, the terminal is here. The initial circuit we just looked at is it has a voltage source and an equivalent resistance in series. Now, when we talk about the Norton equivalent circuit, that Thevenin circuit can actually be converted to an alternative form with a current source this time around that will be in parallel with an admittance, which can be G equivalent, or with a resistance that is in parallel with the current source. This kind of a circuit will be referred to as Norton equivalent circuit, or simply you can call it a Norton circuit or Norton form. So if we are able to create a Thevenin equivalent circuit and we want to write it in a Norton equivalent form, then this V equivalent will be converted to I source, or this V source. This voltage source will be converted to a current source, and that can be obtained by dividing the V equivalent by the R equivalent. We would obtain a current because we know from Ohm's law V is equal to IR. So if you say I is equal to V over R, then it becomes V equivalent divided by R equivalent. You obtain the I equivalent, which is the current source now, and then R will remain this R, or we just find the inverse of this resistance and put it here as the G equivalent, and these two are now in parallel. Here is a Thevenin subcircuit. You can see we have the V Thevenin, which is our voltage source. We have the R Thevenin, which is the equivalent resistance, and you can see we have the voltage here. We have two terminals here, the positive and the negative terminals here, or positive and negative ends. And you can see we also have the current flowing through this resistance. So according to Kirchhoff's voltage law, if we have a closed path here and we draw a path like this, we would have minus Vt plus Rti plus V equal to 0. And then if we make V the subject of that expression, our V would be equal to minus Rti plus Vt, according to Kirchhoff's voltage law. For the Norton subcircuit, you can see we have In representing I Norton, and we have Rn representing R Norton. And then we also have our terminals here, and you can see the flow of current. In this particular case, our In will be equal to, for example, in this particular case, we can apply KCL at this node. When we apply KCL at this particular node, we do know that current entering a node, we assign a negative sign to it, and current leaving a node, we assign the positive sign to it. Okay, so if we do that, In is entering the node, so we can have minus In plus I is leaving the node plus I, and then also plus the current flowing through this resistance Rn. The current flowing here would be equal to V over Rn, because according to Ohm's law, I is equal to V over R. And the voltage seen by this resistance is the voltage V at this terminal. So I flowing through Rn will be equal to V over R. So we have minus In plus I plus V over Rn equal to 0. If you rearrange that equation and take In to the other side, you will be left with In equal to I plus V over Rn, or V divided by Rn. And this is equivalent to, if you rearrange it, it will be equivalent, if you rearrange this equation, it will be equivalent to V equal to minus Rni plus Rnin. Don't forget that we said these two circuits are equivalent. If these two circuits are equivalent and we obtained the V at this terminal to be equal to minus Rti plus Vt, and we also obtained the voltage at this terminal to be equal to minus Rni plus Rnin, we can then equate the two equations and come up with the following expressions. Since Thevenin and Norton circuits are equivalent, it simply means that our RT will be equal to Rn, and then our Vt will be equal to Rnin. Let me connect these dots for you. So if we equate this V equal to minus Rti plus Vt, and then we equate it to V equal to minus Rni plus Rnin. Okay, Rti can be equated to Rni, because this is V, this is V. So the coefficient of I in this equation is minus Rt, and the coefficient of I in this equation is minus Rn. So we can say minus Rt is equal to minus Rn. Therefore, Rt is equal to Rn. This expression holds when Thevenin and Norton circuits are equivalent. Again, we have Vt here, and then we have Rnin here. So we can say that our entire Vt here will be equal to Rnin that we have right here for this expression. And that's exactly what is here. All right. So in case you have a Thevenin circuit, sub-circuit, and you want to convert it to a Norton sub-circuit, these are the two equations you can easily use, and then you can create or establish the Norton sub-circuit or the Thevenin sub-circuit that is given. Or it could be vice versa. You could have a Norton sub-circuit and you will be expected to convert it to a Thevenin circuit. So you know what Rn means. Norton equivalent resistance, In is Norton equivalent current source, Rt is Thevenin equivalent resistance, and Vt is Thevenin equivalent voltage source. You may also refer to these equations as source transformation equations. Here is a simple example we can easily analyze together. Use a series source transformations to find the current I0 in the circuit below. So we have a circuit here, and as you can see, we have a current source to the left and another current source of 4.2 milliamps to the right. The current source to the left is 6 milliamps, as you can see, and then you can see we have I0, which is the current flowing through the 2.7 kilo ohms. Then we have two other resistances in the circuit, the 2.3 kilo ohms resistance and the 1 kilo ohms resistance. So we are supposed to use a series of source transformations to find the current I0 in the circuit. First of all, you want to isolate the left-hand side of the circuit and the right-hand side of the circuit. If you do that, this is what you will have. So you can see that when you isolate this particular side of the circuit, you can see that here, and then you can see this here. So you want to ask yourself, after isolation, what next should you do? When you isolate this circuit, to the left-hand side of the circuit, you can use these source transformations to actually find out what happens next. So we are trying to convert this current source to voltage source and convert this resistance that is in parallel with this current source to a series resistance. When you look at this circuit on its own, it's a Norton equivalent circuit. So we are trying to convert it to a Thevenin equivalent circuit. When you look at these circuits too, it's a Norton equivalent circuit. We want to convert it to a Thevenin equivalent circuit. That's what we're trying to do right now. These will be our voltage terminals. We know that our RT is equal to Rn. So this R Norton, this is R Norton. We can convert it to RT by just equating it using this equation. So our R Thevenin would also be equal to 2.3 kilo ohms, and that's why you have these here. Using this equation, Vt is equal to Rn to find our V Thevenin. To find our V Thevenin, what you will notice is that we know our Rn to be 2.3 kilo ohms, and we know our In to be 6 milliamperes. So multiplying 2.3 by 6 will give us 13.8 volt. But then you have to be very careful, because what you see here is a voltage that is flowing in a downward direction. Our nomenclature for a voltage source is that it should be pointing up, and when it's pointing up, the direction is supposed to be positive. But now this voltage is actually flowing in the opposite direction to our standard direction. So the current is negative. As you can see, this current would be negative. If the current is negative, it means Vt will become minus Rn In, and that's why you have this minus here. Now, if you want to have plus here, all you need to do is just take the negative sign up and bring this positive sign down, and that would accurately represent the flow we have here. If we put positive here and put negative here, then we can leave this as positive. But because our standard expression, our standard symbolic representation for a voltage source is negative and positive up here, which is what we want to keep. Okay, so, and this is not going to support it because it is flowing downward. Current is supposed to go this way. So what we are going to have is this negative sign here. Please make sure you understand this properly. This is very important. And then we have converted this northern part of the circuit to a Thevenin equivalent here. What about this other part? You can see here that the 4.2 milliamps is actually taking the standard representation of our current source. Hence, we're going to have, if we're going to have a standard representation of our voltage source, the voltage is going to be positive because we expect current to be flowing in this direction. And representing that with the voltage source, will have a plus right at the top here and negative right at the bottom here. So again, our RT is equal to Rn. It means this resistance RT will be equal to 1 kilo ohms, and our Vt will just be 4.2 milliamps multiplied by 1, and that gives us 4.2 volts. As you can see, we have further reduced this complex circuit to something simpler than what is given. 1 kilo ohms, 2.3 kilo ohms, and 2.7 kilo ohms are now in series. If resistances are in series, you add them together. So this gives us 2.3 plus 2.7 plus 1, and that should be 6 kilo ohms. That's exactly why we have 6 kilo ohms here. Don't forget, the I naught is still retained, and it's flowing in this direction. Now we have two voltage sources. The first one is minus 13.8 volts, and the second is 4.2 volt. How do we combine these two voltage sources into a single voltage source? Now, we have what we refer to as series aiding voltage sources and series opposing voltage sources. Series aiding voltage sources are series connected sources with their polarities connected so that the plus terminal of one is connected to the negative terminal of the next, allowing current to flow in the same direction. Okay, in that particular case, you will add the voltage sources together. So when you have voltage sources, two voltage sources where the plus terminal of one is connected to the negative terminal of the other, you have what we refer to as series aiding voltage sources, and in that case you add them together. All right, in this particular case, you can notice that the plus terminal is connected to the plus terminal of one voltage source is connected to the plus terminal of the other voltage source. So this cannot be said to be series aiding voltage sources. Then the second we have is the series opposing voltage sources. The series opposing voltage sources are series connected sources which have their polarities connected so that the plus or negative terminal of one source is connected to the plus or negative terminal of the other source. So when the plus terminal of one source is connected to the plus terminal of the other source, we have what we call the series opposing voltage sources. In that particular case, the currents are not flowing in the same direction. In the case of series aiding voltage sources, where we have positive of one source connected to the negative of the other source, it allows current to flow in one direction. But in the case where we have the positive terminal of one voltage source connected to the positive terminal of the other voltage source, or we have a negative terminal connected to the negative terminal of the other voltage source, it is called series opposing voltage sources, and in this particular case, the currents are not allowed to flow in the same direction. That connection does not allow current to flow in the same direction. So in this case of series opposing voltage sources, we subtract the smaller voltage from the larger voltage. And then the final answer, of course, will take the polarity or the sign of the larger voltage. All right. Now there are two ways. There are two ways to solve this problem. The first way would be to apply KVL. If you apply KVL here, and then we have our flow of current this way, this is what we are going to have. Okay, we are coming, let's say we're traversing 4.2 volt on the positive end. So we're going to have 4.2 is going to have a positive sign. And then if we are traversing from negative upward here, this becomes minus. And then we open a bracket. The value of that voltage is minus 13.8 volts. And then if we are traversing this resistance, don't forget this is a positive sign. So, and the flow, the path of our current is actually going up here. That simply means what we're going to have here is minus 6I naught. Everything will be equal to 0 if we apply KVL here. So applying KVL will give us 18 equal to 6I naught. And our I naught, if you divide both sides by 6, our I naught will be equal to 3. This is 6K, by the way. So I naught will be equal to 3 milliamperes. This is the first method you can use to solve this problem. All right. Now let's apply the second method and see what comes out of it. So as you can see, we have minus 13.8 volts, we have 4.2 volts, and then we have the 6 kilo ohms resistance right up here. So let's go ahead and combine these two sources as discussed. We subtract the smaller from the larger. In this particular case, the smaller voltage would be 4.2 and then the larger is 13.8. Okay, this negative sign here represents the fact that current is actually flowing in the opposite direction. So we have minus 13.8 minus 4.2, and that gives us minus 18 volts. Okay, so if we have that, this is exactly what we have. We have minus 18 volts right here. Now, if we have minus 18 volts here, the next thing to do is just to apply our Ohm's law, which says V is equal to IR to find our I naught. All right, since we already know that our volt is minus 18, what is our I naught? Don't forget that with the plus sign here, and I naught coming to this particular direction, I naught is going to have a negative value. Okay, if this arrow of I naught were to be going in the opposite direction, then I naught is going to have a positive value. But because I naught is actually coming in this direction, all right, and then we have a plus sign right up here, it simply means that our I naught is actually a negative, is going to have a negative sign. All right, so we can say that minus I naught would be equal to V over R. Our V is minus 18. So minus I naught would be equal to minus 18 over 6. Minus would cancel minus. I naught will therefore be equal to 18 divided by 6 kilo ohms, and that gives us 3 milliamperes. This is the first method you can actually use to find your I naught. If you choose to use a second method, you will still obtain the same thing. Otherwise, you can also apply KVL to this circuit and draw your closed path flow of current in the clockwise direction. If you do that and you apply KVL, your KVL tells us that when we are traversing from negative to positive, it becomes the voltage is going to take a negative sign. So this becomes minus 18 volts minus 6 kilo ohms multiplied by I naught equal to 0. Then you make I naught the subject of the expression. It becomes I naught equal to 18 divided by 6. In that particular case, you will still obtain 3 milliamperes, no matter what the situation is. All right, let's move on. Please go over this example again and again so you can have a better understanding of what we are talking about. You don't want to be caught unawares. And if you do have any questions, you can always ask them here. You can always reach out to me and we can find a way to solve, to clarify any doubt that you have. If the circuit terminal law is extracted as a linear equation, then RT and VT are slope and intercept respectively. Okay? From basic knowledge of mathematics, this should be straightforward. If we have V equal to F of I, where V is a function of the current, that's what this means, and then we have our, of course, this is our terminal. F of I, the function F of I will be equal to minus RTI plus VT. We have said V is equal to F of I. So we are replacing the V that should be here with F of I. These are Thevenin parameters as we know. And then we know Rn equal to RT, In equal to VT over Rn. We know these are Norton parameters. It follows that if V Thevenin is equal to F of 0, that simply means when the current is 0, when we have an open circuit and the current is 0, we are going to have V open circuit. That's what it simply means. When the current is 0, we are going to have open circuit. And we can say that our V Thevenin will be equal to the open circuit voltage. All right? So as we continue to work on, you will begin to find out that we can actually decide to open the circuit if we want, depending on how simple we want to make our circuit to eliminate the complexities that we are presented with. One could open circuit the terminals to find VT. This is what simply means. Once you open the circuit, then you're going to be able to find your VOC. And once you find your VOC, automatically your VT will be equal to your VOC. Okay? It also follows that F of I equal to 0. In this particular case, if we say that F of I is equal to 0, that means we are saying that VT is equal to 0, all right? It simply means we are shorting the circuit. In that particular case, what you would have is that minus RTI plus VT would be equal to 0. And once V is equal to 0, it simply means we have a short circuit. And in that case, our I becomes ISC, I short circuit. That is why you can see we have I short circuit here. And then if you rearrange that, your RT will therefore be equal to VT divided by I short circuit. Your VT, we have found it to be VOC. You can put VOC here. We have our I short circuit here. And our I short circuit automatically will be equal to our IN, which is the I nothing. All right. So our R Thevenin, if we are looking for R Thevenin, when we short circuit the circuit, we can obtain that by writing RT equal to VOC divided by I nothing. So one could short circuit the terminals to find I nothing and R Thevenin once VOC is known. Okay, so please pay attention to this. Don't be confused at all and try to focus on what matters and simplify whatever needs to be simplified in your mind. However, if you do have questions regarding any of this in your mind, feel free to reach out to me by all means necessary. So let's quickly look at what we have here. Thevenin and Norton equivalent circuits can be obtained by applying any two of the following three steps. Applying all the three steps is not necessary, but if you have the time and then you want to, go ahead and apply all the three steps, the ball is in your court. However, applying just two of any of these three steps would be okay to deal with any Thevenin or Norton equivalent circuit that we have. The first step is you open circuit the terminals and calculate the open circuit voltage. This we have learned how to deal with, how to find the open circuit voltage and what that means. We have talked about that in this lesson and even in previous lessons. Then the second step is to short circuit the terminals and calculate the short circuit current, which is the same thing as the ISC. You know what that means, and then you know exactly how to find that when we have a short circuit. When we short circuit, Thevenin equivalent may then be found from VT is equal to VOC, since we have said earlier that VOC is equal to VT when we open the circuit. And then once we know that, and our RT will be equal to VOC over I short circuit. And Norton equivalent may then be found from IN is equal to I short circuit, because from here we can find our I short circuit since our VOC is known and then our RT is known. So we can easily find our I short circuit from here. If RT is not known, we know that our RN is equal to RT. So we can use that and say since Rn is equal to RT, that would also be equal to VOC over I short circuit. So we can go ahead and then find whatever is missing using any of these equations that we have here. So if you are using step 1 and step 2, you can find anything that is missing. However, if you choose not to use step 1 and step 2 together, probably you just want to use one of the steps and the third step. We can go ahead and discuss the third step right away. Alternatively, equivalent Thevenin resistance RT and Norton resistance Rn can be computed as the resistance looking into the terminal of the circuit when all internal sources have been killed. In this particular case, that simply means your aim is to kill all internal sources. Killing them simply means you're shutting them down. In this particular state, independent voltage sources are replaced with short circuits and independent current sources are replaced with open circuits. This method can only be used when there are no dependent sources in the circuit. So our RT would be equal to Rn and will be equal to R equivalent with sources killed. It simply means that when you have a circuit and you have current sources and voltage sources, you can replace the voltage sources with short circuit and replace the current circuits with open circuit. When you do that, it simply means you are shutting them down. You are killing the internal sources or you are shutting them down. When you do that, the only thing you will be left in that circuit will be the resistances or the loads. You can then go ahead and find the R equivalent in the circuit. Once you find your R equivalent, that R equivalent will be the same thing as your R Thevenin and will definitely be the same thing as your R Norton. And this method can only be used when we do not have dependent sources in the circuit, because we cannot shut dependent sources down. Dependent sources cannot be shut down. However, if all we have is independent sources, be it current or voltages or both of them, we can kill them or shut them down, find our R equivalent, and then once we know the R equivalent, we know that is equal to R Thevenin, and we can easily find our VOC, and then we can do whatever it is we want to do and find whatever terms that are missing. All right. When there are dependent sources on the circuit, what do we do? Enhance the previous method, which is the method that has to do with killing the internal sources, by a test-like procedure. The first thing you do is you deactivate all the dependent sources. Do not deactivate dependent sources. Okay, you only deactivate the independent sources. Then apply a test voltage called, you can label it VT, and a test current IT, which you can also label IT. You can apply both to the terminals of interest. The terminals of interest, the terminals whose values we're looking for. Once you have done that, you can solve the circuit by finding the ratio between the two test parameters to get the effective resistance in the circuit. So that simply means your R Thevenin will be equal to the V test, the test voltage, divided by the test current. And once you have that, you can go back up here and use all the other equations we have to find all the values that are missing. Here is a Thevenin equivalent example, a hypothetical example for Thevenin equivalent circuit. And we'll try to look at how this method is applied using all the three methods that we just talked about. So this method does not have any dependent sources. We only have independent sources. So with these independent sources, we are just going to use the following methods. First of all, let's say this is a circuit given to us. We have terminal A and B. We have the independent source voltage, and then we have the resistances given in the circuit as follows. Open circuit the terminal AB of the given circuit. Once you do that, it becomes easy to find your R equivalent. Once you open this circuit, what you're going to have is going to be R equivalent, and then you're going to be able to find your R equivalent, and then you have your V equivalent here. Okay, this is what that looks like. Once you find your R equivalent, the next thing you want to do is to calculate the voltage VOC seen at the terminals AB. We open this particular circuit, and then you find the voltage VOC seen at this particular terminal. How do we do that? Okay, first you open the circuit at this terminal, and after you have done that, you calculate the open circuit voltage seen at the terminals A and B. Once you have done that, remove or kill all the sources in the circuit. Once you are done with that process, you can go ahead and then calculate RAB, which will be equal to the R equivalent, and then you will be done with virtually anything that you are asked to do. Eventually, this is where you're going to arrive at. Once you do carry out all these four processes, you're going to arrive at this circuit eventually. So let's begin from the beginning. So once you open this terminal, it simply means you can then see that R3 and R4 are in parallel. If R3 and R4 are in parallel, you treat them like that, and that becomes R3 multiplied by R4 divided by R3 plus R4. That gives us the equivalent for this circuit, and that's exactly what we have here. R3 parallel R4. That's what we have. Okay? And once we do that, what you would find out is that since this circuit is open, the current flowing through R1 will be equal to current flowing through R2, and will certainly be equal to the current flowing through R3 parallel R4. This simply means that R1 is now in series with R2, R2 is now in series with R3 parallel R4. In that case, this is what you're going to have. R1 is in series with R2, which is also in series with R3 parallel R4. Okay, this particular circuit here is equivalent to this circuit you're looking at. Okay, this is the simplified circuit, and it is equivalent to this circuit. So depending on how you choose to draw it. All right, now we need to calculate VOC between terminals A and B. The VOC between terminals A and B. This is going to be easy to calculate because we can see R2 will see VOC, okay? R2 will see the voltage VOC. So if we use voltage division, we can easily find the voltage across, we can easily find our open circuit voltage, which will also be equal to V2. Because R2 will see VOC, so the voltage across R2 will be equal to the voltage VOC. So we can easily find that. Okay, so if we do that, this is what we have. Using voltage division, we can say that our VOC will be equal to the voltage source, which is VS, multiplied by R2 divided by the equivalent resistance in the circuit. The equivalent resistance in the circuit, like we said earlier, is R1 plus R2 plus R3 parallel R4. That is the equivalent resistance in the circuit. And since we're looking for VOC, and we know VOC is also equal to V2, like we mentioned, it simply means that our VOC equal to V2 will be equal to R2 divided by R equivalent multiplied by the voltage source in the circuit, or the input voltage. Okay, if we do that, we will have obtained our VOC. or the open circuit voltage. Then the next thing you want to do is to remove all the sources in the given circuit. Okay, so when you remove all the sources, it means that you are shutting the circuit down. For voltages, it simply means you are short circuiting it, and then for current, it simply means you are opening the circuit. So what we do have is a voltage source. So you short circuit this branch of the circuit. Okay, when you do that, it simply means this voltage source is no longer there. But when you have a current in place of voltage, let's assume what we have is current source, not voltage source. What you will do is to open the circuit. So to open the circuit means you are killing the source. You are shutting down the current source. And to do that, you open the circuit. And this is what the circuit will look like when you do that. So this is what happens when you short the circuit. When you short the circuit, you have, this is short. So you have R1, you have R3, and then you have R3 parallel R4 here. What you would find out is that whatever current comes into this R3 parallel R4 will be equal to the current passing through R1. So R1 and R3 parallel 4 are in series. So you can see we have R1 plus R3 parallel R4. Okay, now you will then see that R2 is in parallel with R3 parallel R4 plus R1. So I will treat them exactly like that. So what you will find is that our R equivalent will be equal to R3 parallel R4 plus R1 parallel R2 will be the equivalent resistance in the circuit. So if you do that, you're going to open R equivalent like this, okay? It's going to look a little bit complex because we're not dealing with raw figures, but when we start dealing with raw figures, all of these are going to be more simplified. So since we have found our R equivalent and we have found our VOC, we do know that our VOC is equal to V Thevenin. Our R equivalent is equal to R Thevenin. Okay, so that means we can easily find our Thevenin equivalent circuit by just putting the VOC value we obtain here and then the R Thevenin value we obtain, we put it here. So if we choose to use the open and short circuit tests, how do we go about it in case we have a question in that direction? This is what we do. Short circuit the terminal A and B and measure I short circuit. Okay? And then open circuit the terminals A and B and measure VOC. Don't forget, here we are carrying out tests. So the first test would be to short circuit terminals A and B. This is terminals A and B. When you short circuit it, you can easily measure your I short circuit using an ammeter, and then you record your value. Again, after that, you open circuit the terminals A and B, and with that, you can use a voltmeter to measure your open circuit voltage. Okay, once you do that, the next thing you want to do, so once you know your short circuit current and then you know your open circuit voltage, many things become easier. Now, what is the objective of the short circuit test? The objective of the short circuit test is to determine the short circuit current flowing when the terminal A and B are shorted. The procedure to do that is to short circuit the terminals A and B of the given circuit. Measure the I short circuit flowing through the short circuit, just like we mentioned earlier. And that's exactly what is going on here. Okay, this is exactly the same question given to us with this terminal. We are just shorting this circuit, placing an ammeter right here to measure the short circuit current. Okay, now the short circuit current is given as Vs over R1 plus R3 parallel R4. Right, why do we have this here? Don't forget that our current is equal to voltage divided by resistance. So when we short this particular circuit, it simply means that R2 becomes so large that no current can pass through it. So all the current coming from Vs passing through R1 will go through this terminal. This is a short circuit. To short circuit terminals A and B, you place a conductor here, and that conductor can accept maximum allowable current to pass through it. And this becomes so large, R2, that's how to short this circuit. This becomes so large that no current can flow through it. So all the current coming to R1 will not be able to branch through R2. It just goes through to terminal A down to terminal B, and then it goes through to this parallel circuit. This R3 and R4 are still in parallel, so you can convert them to one single resistance and call it R3 parallel R4. So the current coming from terminal A through B will pass through R3 parallel R4, okay? And that means R1 and this parallel circuit here are in series. So that is why the equivalent resistance in this circuit, after you short circuit terminals A and B, will just be R1 plus R3 parallel R4, because R2 has become so large, and so it will be treated as redundant in the circuit because no current is passing through it. The current passing through it is 0. And when the current passing through it is 0, it simply means there is no voltage across R2 anymore. So R2 is rendered redundant in this particular circuit. So easily we can calculate our I short circuit will therefore be equal to the voltage, which is the voltage source, divided by the equivalent resistance in the circuit. When we open the circuit, what is our objective? The objective is to find the open circuit voltage when we carry out an open circuit test. Okay, we want to open the circuit and then we find the open circuit voltage. When you open this circuit, it simply means no current can pass through this terminal when you open this circuit. Okay, and all you need to do is to measure the open circuit voltage. Okay, and that open circuit voltage will be the voltage seen by this resistance R2, all right? But no current will pass through this terminal. That would mean that all the current flowing through VS, flowing from VS through R1, will pass through R2. And once they get to R2, since we know R3 and R4 are already in parallel, all right, so this becomes R3 parallel R4. We can represent that with just one single resistance. So R1 is now in series with R2, which is now in series with R3 parallel R4. That is why the equivalent resistance in the circuit now becomes R1 plus R2 plus R3 parallel R4. So if we applied voltage divider and we are looking for VOC, we had said that VOC would be equal to V2 because R2 would only see VOC. So VOC will be equal to V2. So our VOC, which is equal to V2, using voltage divider, would now be R2 divided by the equivalent resistance in the circuit multiplied by the voltage source. And that is how we can find our VOC. So once we obtain our VOC, and we have also obtained our I short circuit, then we can go ahead and divide the VOC by the I short circuit. In that way, we would have found our R equivalent, and our R equivalent would be equal to our R Thevenin. And once we know those, we can go ahead and find our V Thevenin, because V Thevenin already will be equal to the VOC that we found. So V Thevenin will be equal to VOC, which is also equal to V equivalent. So in any case, at the end of the day, we are going to end up with this Thevenin circuit. Whatever method we choose to use, if we use the test current and test voltage method, or we choose to use the other methods, the first method, whatever we choose to use would arrive at the same Thevenin equivalent circuit. And of course, the same values for VT, for RT, for RN, for VOC, and our R equivalent. So here is a second example we can look at, and this second example actually has raw figures. So we're going to quickly use this to demystify whatever questions you probably have in your mind. Find the Thevenin and Norton equivalents of this circuit. So you can see we have a voltage source here, we have 3 resistances, and we have a terminal voltage here. The first step will be to open circuit the terminals. When we open circuit this terminal, that means we are setting I to be equal to 0. That way we can find our VOC, which is the open circuit voltage. When you open circuit, this is what we have. It means all the current coming through here will not be able to pass through this terminal. All right. So that simply means we are rendering these 6 ohms redundant because no current will pass through here. The currents coming here will be 0, so the voltage across these 6 ohms will be equal to 0. If that happens, it simply means that 4 and 12 are now in series. If 4 and 12 are now in series, we can then go ahead and find the voltage V1 that is seen by this resistance 12 volt. To do that, that becomes VOC is equal to V1, because V1 will be equal to VOC, by the way, they are in parallel. VOC will be equal to V1, which will be equal to the voltage source VS, that's 24 volts, multiplied by R1, which is going to be 12 ohms, divided by the equivalent resistance in the circuit, which will now be 12 plus 4, because these are now in series and this is redundant in the circuit. If we do that, we would obtain our VOC to be equal to 18 volts, and that is Thevenin already. The next thing we will do is to short circuit the terminals. When we short circuit this terminal, it simply means that our I short circuit will be available, but voltage will be equal to 0. V would be 0. When you short circuit the terminal, this is what we have. You place a conductor on the two terminals. So we have I short circuit flowing this way, maximum current possible. And when that happens, it simply means that there is no current that will be able to flow through this 12 ohms resistance. All the current coming from here would flow through the 4 ohm resistor and then flow through the 6 ohm resistance. So first of all, it simply means that when there is a short circuit here, 6 ohms and 12 ohms are in parallel, first of all. So when they're in parallel, what we have is R6 parallel 12 ohms will be equal to 6 times 12 divided by 6 plus 12. That gives us 4 ohms. So if we combine these two, because they're in parallel, we then have 4 ohms. These 4 ohms we have will now be in series with these other 4 ohms that we have here. So our V1 will therefore be equal to, using voltage divider, our V1 will therefore be equal to the V source multiplied by R1. In this case, R1 is now 4 ohms because we have combined 6 and 12 together. So the resistance across this V1, right, the resistance connected to this V1 will now be the combination of these 6 and 12 ohms, which is 4 ohms. So we now have 4 at the top here divided by the equivalent resistance in the circuit, which will be 4 plus 4, because 4 plus 4 will now be in series. The 4 we obtained after we combine these resistances that are connected in parallel is 4. So 4 plus 4 will give us 8, and then we can find our V1 to be equal to 12 volts. So once V1 is equal to 12 volts, it simply means that it's easier now to find our I short circuit. How do we find our I short circuit? That would be equal to the voltage seen by these 6 ohms, which will now be V1, divided by this resistance. That voltage is 12 volts that we just calculated here, divided by this resistance, which is 6 ohms, and that gives us 2 amperes. I'll take that again for easier understanding. We are looking for I short circuit. I short circuit is passing through 6 ohms resistor. Okay, so that simply means we have this R and we're looking for this I. All we need now is a voltage, and then we'll say our I short circuit will be equal to that voltage divided by this resistance. The only voltage seen by this 6 ohms resistance is the V1. And since the only voltage seen by this resistance 6 ohms is the V1 connected to this 6 ohms, then we can say that our I short circuit will be equal to 12 volts divided by 6 ohms. Don't forget that 6 ohms and 12 ohms are in parallel. And when they're in parallel, it simply means that the voltage across both of them are going to be the same. Hence, we can have I short circuit equal to 12 volts divided by 6 ohms, which will give us 2 amperes. So our I short circuit is equal to 2 amperes. Our V open circuit, we obtain that to be equal to 18 volts. Once we have that, it then becomes easier to find our R Thevenin. R Thevenin will be equal to V open circuit divided by I short circuit, and that gives us 18 divided by 2, and that is equal to 9 ohms. Take your time and go over this example again. Understand everything that you can understand from this particular example. If peradventure there are questions in your mind or there are things you do not understand, do not hesitate to reach out to me as fast as possible through any means, either via the comment below this video or via other means. Make sure you reach out to me and I will be able to clarify whatever it is that you have doubts about. So we can then go ahead and draw our equivalent circuit. We already found out our I short circuit is 2 amperes, our V open circuit is 18 volt, and we know our V open circuit is the same thing as V Thevenin. We already found our R Thevenin to be equal to 9 ohms. So drawing the equivalent circuit will mean that we are using 18 V Thevenin and RT, which is 9 ohms for the Thevenin equivalent circuit. And that's what we have here. V Thevenin is 18 volt, R Thevenin is 9 ohms, and this is the Thevenin equivalent circuit. Now to find the Norton equivalent circuit, and we already mentioned earlier that our I short circuit is equal to the I Norton, the Norton current, okay? So with that, we say our I Norton is equal to 2 amperes, and since we know our RT is equal to RN, and that equals 9 ohms, this becomes our R Norton, 9 ohms. And in Norton equivalent circuit, the current is in parallel with the resistance. So this is exactly what we have here. And that's why we have exactly this circuit here as the Norton equivalent circuit and this as the Thevenin equivalent circuit. Beyond asking you to find the Thevenin voltage, the equivalent resistance or Thevenin resistance and the I short circuit and all of those parameters, they may ask you to actually draw the Thevenin equivalent circuit or Norton equivalent circuit or both of them. This is where we'll end this lesson. I would encourage you to subscribe to this channel in case you have not done so. Give this video a thumbs up if you like it, and don't hesitate to let me know what you think about some of the examples, some of the explanations, some of the concepts discussed. Whatever you think about this video, please drop them in the comment section. I would love to read from you. Thank you for watching. Thank you for learning. I'll see you in the next lesson.